Welcome back to Chapter 10 notes. We are going to start them over. I know we did some before break, but it's been a wild ride. So, Chapter 10, waves. Here we go. Waves, what are they? It says waves are a repeating disturbance or movement that transfers energy through matter. The big deal there is transfers energy. That's the part we care about. It's the whole reason a wave exists, is to move energy from one place to another. Examples of waves, I know we talked about this a little bit in class, but waves don't just have to be water waves, although ocean waves are an example of that, right? They transfer energy through the water. There's lots of different kinds of waves. So earthquakes transfer energy through the ground in the form of waves. Light transfers energy through empty space in the form of waves. There's lots of options. That's just three, but a couple good examples. How are waves formed? Well, another example going back to the water, it says if you drop a rock into a pond, the energy in the falling rock is transferred into the water. That energy spreads out in the form of a wave. In other words, a wave is formed by imparting energy into something, right? So if we put energy into an object, theoretically, that object can have a wave move through it. For example, a slinky. If you push into a slinky, that slinky is going to have that energy travel down the slinky in the form of a wave. So waves are just formed when energy is imparted on something, and they are the method of travel for that energy. Waves transfer energy without transferring matter. This is also a big deal. We mentioned waves are designed for energy transfer. I think I've said that like 7 times now. Sorry. But what waves do not transfer is matter. They carry just the energy. So if there's a boat on the water, the wave will carry energy past the boat, but the boat will remain relatively in the same place. That does not mean that boat can't use the energy. It's what surfing is, right? Surfers are trying to ride the energy of the wave. But unless we are actively trying to do it, the energy itself is not going to move the boat. We have to harness that energy in order to use it. So it says if a boat's on water, the wave won't carry the boat, only the energy. More about waves. It says all waves are produced by vibration. So matter traveling through the wave is known as the medium. Sorry, the matter the wave is traveling through. So whatever a wave goes through is the medium. If the wave is traveling through water, we call that the medium. If the wave is traveling through sand, that's the medium. Whatever the wave is traveling through, that's called the medium. And there are some waves that don't require something to travel through, and that's electromagnetic waves. So things like light and radio don't actually have to travel through anything. They don't need a medium. Most waves need a medium, but there are a couple that don't. So mechanical waves. So, like I said, the vast majority of waves require a medium, and those waves are called mechanical waves. Any wave that needs a medium is called a mechanical wave. So mechanical waves are waves that can only travel through a medium, it says that at the top, and they come in two varieties. There's what we call transverse waves, which are the up and down waves. That's the top ones over here, right? And there's what we call longitudinal waves, which is the bottom one on the right here, which go back and forth. Sometimes longitudinal waves are called compressional waves or compression waves because we are compressing something and letting it spring outward. So that works with things like springs, slinkies, etc., but also, for example, waves in the air. Air molecules are bumping into each other in the form of compressions. That's how sound waves work. So that's how we hear things. So transverse waves, type number 1, those are the up and down waves, and then longitudinal waves, type number 2. Those are the back and forth waves. Excuse me. So let's start with transverse waves, since they were the first ones we mentioned. And remember, transverse waves are moving the energy in an up and down pattern. So it says a transverse wave, matter moves back and forth at right angles to the direction the wave travels. In other words, if our energy is going left and right, that means the wave is going up and down. So in the case of the water here on the left, notice the waves are rhythmically going up and down. But again, the matter should not move just the energy. So the energy follows that wave, and you notice the wave goes all the way through to the right. But the boat itself, or the toy boat, it says up at the top, doesn't move. It just kind of cycles with the wave. So it ends up where it started. and that's because it would have to actively work to follow that energy of the wave in order to use it. It can use the energy of the wave, but unless it's prompting itself to do so, it's not going to. So again, transverse waves, right angles to the direction the wave travels. So if the energy is going left and right, the transverse wave is having up and down pulses. Then let's move on to compressional waves. Again, those can be called compressional or longitudinal. Either name works. And a compressional wave is just when matter moves back and forth along the same direction the wave travels. So in this case, the slinky, again, our coil of springs is going to start in a location, and when we let go, that's going to bounce down, but eventually the springs are going to return to the same starting point. So a good example of this is waves traveling along slinky, right? And the energy is going to go in the same direction as the matter. So energy goes to the right, matter goes to the right. Eventually that matter is going to spring back to the left, but the energy is still going to have traveled down the slinky. Sound waves. We mentioned sound waves were a good example of a compressional wave. And the reason they don't just call them longitudinal all the time, the reason they call them compressional is because sometimes the waves travel in compressions. So up here on the top, we have an example of a compressional sound wave, where these little dots are meant to be air molecules, and those air molecules are congregating in chunks, right? Because there's energy there. What's happening is our speaker vibrates, and that vibration bumps some air molecules forward. Those air molecules bump into each other in a cluster and are going to shift that cluster along the air, right? Air molecules are going to bump into the air molecules in front of them, and then those will bump into the air molecules in front of them, and that chain reaction will transfer down the line. So eventually, those air molecules will bump into our eardrum, vibrate it at the same rate the speaker was vibrating, and that's how we get sound. So we call those compressional waves because it works in a series of compressions. Over on the left, it says sound waves are compressional waves. We just said that. They are formed from vibrations in nearby molecules of air, but can also travel through liquid or solid mediums such as water or wood, right? We've been able to hear sound underwater if you've ever played around and screamed at your friend in a pool. It says they're able to travel through these denser materials because the particles are pushed together and move apart as the sound wave travels through them. So sound actually travels faster through denser materials like water and wood, which is why when somebody knocks on a door, you hear that clack, clack, clack. But keep in mind, it also has to travel through the air behind the door before it gets to your ear. So if your ear was up against the door, you'd hear it immediately, but there is some leeway there. But sound travels pretty fast in general. So sound waves are compressional waves. That's the takeaway here. Water waves. Since water waves move up and down and slightly back and forth, creating a somewhat circular pattern, an object in the water will bob in the circle. So we kind of had this example with the toy boat, but in a transverse wave, that matter won't stay perfectly still, right? It will end up where it started. So we had our toy boat start here at the bottom of our trough here in the wave. But eventually that boat is going to cycle back to where it is. But notice there is a circular pattern in the motion, and that's because the wave is cyclical, right? Waves go in pulses. So on, off, etc. Most waves are going to operate this way. Last slide, OD Day. Earthquakes. So it says seismic waves are a combination of transverse and compressional waves, and the Earth absorbs energy from the wave, causing it to move and shake violently. So I don't know if you can see it here, but there is both compressional and transverse waves. So the compressions would be the vibrations moving up from the epicenter of the earthquake on the ground, and then there are transverse waves also moving out from that. And at ground level, typically it's transverse waves, which is why we get that shaking up and down of the ground around us, and kind of what makes an earthquake scary. So it's not that all waves are either compressional or transverse. A lot of times we can have mixtures of both. Usually it's one or the other, but we can mix them both into a scenario. So thanks for watching, guys. Hopefully this wasn't too terribly agonizing, and enjoy the rest of your day.